Look at this example. In this case, we have a counter flow heat exchanger. So we would like to heat water with geothermal water. So the cold water at 20 degrees Celsius and 1.2 kilogram per meter per kilogram second mass flow rate enters into system, and we want to reach 80 degrees Celsius with this water. And available hot water is geothermal hot water is at 160 degrees Celsius at a rate of 2 kilogram per second, and we know the diameter of the tube is 1.5, and overall heat transfer coefficient is given, which is 640 watt per meter square. So the question is, what should be the area and length of this heat exchanger to carry out this operation? To make sure the outlet water, we can heat it up to 80 degrees Celsius. Let's start with, so what do we know? So we know T cold in, T cold out, T hot in, and we also know overall heat transfer coefficient, and we also know the diameter. So what are we trying to find? Find this surface area and length. So let's start with our assumptions. What are our assumptions? So let's assume this is a steady process, steady state. We'll assume heat exchanger is well insulated outside. There is no fouling. And the fluid properties are constant. Okay. So let's start with the analysis. At this point, we know the mass flow rate for both sides, hot and cold side, but we don't actually know the outlet temperature for the hot side. So we'll be using the thermodynamical balance. Q is equal to M, heat transfer is MCP, T out minus T in for water. This is also equal to M geothermal water, CP, T in minus T out, geo. So the first question here, question number 1. CP at what temperature? What temperature do we evaluate CP? So you see, so we go from 20 to 80, and we don't know the average, so we'll assume an average temperature, T bar, M, which is 20 plus 80 over 2, 50 degrees Celsius. We will evaluate the properties for water, 50 degrees Celsius. So that means at this point, the CP is equal to 4180 joule kilogram per Celsius. So we can calculate Q based on this information. Mass flow rate for water is 1.2 kilogram per second. CP is 4180 joule kilogram per Celsius. The temperature difference is 80 minus 20. So this is in Celsius. So this is 60 degrees Celsius. So we have 301 kilowatt. So now our goal is to find the outlet temperature for the geo water. So Q is equal to M geo CP T in minus T out geo. So that means T out is equal to T out is equal to Q dot over M GOCP. This is minus plus T in. T in is 160 degrees Celsius. Q is 301 kilowatt. mg is 2.5, so 2 kilogram per second. Now we go back to CP. At what temperature do we evaluate the CP for geothermal water? What CP should we use here? At 160 degrees Celsius, CP is equal to 4.33. At 20 degrees Celsius, this is the lower bound, 4.18. This is kilojoule, kilogram per Celsius, kilojoule, kilogram per Celsius. So we can just assume it's average of these two. So this is 4.26 kilojoule per kilogram per Kelvin. So we need to do iteration, but let's start our analysis with the average of the coldest possible CP and hottest possible CP. So this is 4.26. If we use 4.26 or 4,000 joule per kilogram per Celsius instead of kilojoule, so we get a T out. T out turns out to be 124.8 degrees Celsius. And if you look up the properties at 124.8 Celsius, so you'll get you need to calculate C average, T mean, so 124.8 plus 160 over 2. So T mean is 142.4, and CP at this point is, CP at 142 is 4.28 kilojoule kilogram per Celsius. So this is not bad. So again, when we are looking up the properties, we have to look up the mean of inlet and outlet. So inlet was 160, outlet is 124.8. So the mean temperature is 142, and CP at this point is 4.28, which is very close to what we initially assumed. So this means our assumption was not bad. So that means the outlet temperature is 124.8. So outlet temperature is 124.8. So that means, so we know all 4 T's temperatures are known. So now let's calculate delta T1. So again, this is counterflow. T hot in, T cold out, T hot out, T cold in. So this is the profile. So delta T1 is delta T hot in minus T cold out, T hot in minus T cold out. So T hot in is 160 degrees Celsius, T cold out is 80 degrees Celsius. So difference is 80 degrees Celsius. Delta T2 is T hot out minus T cold in. So T hot out is about 125. T cold in is 20. So the difference is 105 degrees Celsius. So that means I can calculate the log mean temperature now. I can calculate the log mean temperature. So delta T log mean is delta T1 minus delta T2 over ln delta T1 over delta T2. So that means 80 minus 105 divided by ln 80 over 105. So you get 92 degrees Celsius. So now we remember Q is equal to U times AS times delta T log mean. So that means AS is Q over U delta T log mean. And Q we calculated above from MCP delta T, which is 301 kilowatt. So that means 301,000 divided by U was given watt. This is watt, meter square per Celsius. And log mean is 92 degrees Celsius. So if you carry out this, you'll get 5.11 square meter as the area surface. And if you want to calculate the length, A surface is pi dl. So L is AS over pi d, which is 108 meter.